All right. Good afternoon, everybody, and greetings from sunny California and Mountain View and the home of the SETI Institute. And I'm joined here by my friend and colleague, James Parr, the CEO of Trillium Technologies. And we're going to tell you an interesting story today about a fantastic program we've been running in partnership with NASA and private industry over the last several years called the Frontier Development Lab. And it starts with a story sometime in October of 2015, when I was sitting in my office at the Institute and got a phone call from the office of the chief technologist at NASA headquarters, which was interesting enough. I was really only a few months into my new position at the SETI Institute. So I took this call, and the gentleman on the other end of the line said, "Hey, we'd like to talk to you about a really interesting idea we have. We've got a few questions we want to explore. And we want to talk to you about partnering together to explore these questions." And the first question was, we're interested in whether machine learning and artificial intelligence tools and techniques can be applied to support and enhance NASA science and NASA research. We have another question as to whether or not we can put together interdisciplinary teams of experts in the machine learning and artificial intelligence area, paired off with domain scientists in particular areas of scientific research relevant to NASA, and do meaningful interdisciplinary team-based programs in a very intense research sprint over the summertime. And third, we're kind of interested to know if we could engage private industry in a public-private partnership to pursue this program and have private industry bring in technology and subject matter experts and algorithms, state-of-the-art capabilities in machine learning and artificial intelligence. And in what I still consider to be the shortest decision of my career, about 3 nanoseconds, I said, "Yes, that sounds like a great idea. How can we help you?" And the question was whether or not the SETI Institute could basically manage and host this program for NASA and with NASA, and also be a place where we engage private industry to bring this program to life. And in the following summer of 2016, what is now known as the Frontier Development Lab, or FDL, was launched, and the first ever set of research challenges bringing AI and machine learning tools and techniques to planetary defense and the study of asteroids was launched. And a principal protagonist, if you will, in this whole endeavor was James, who you see here today, who was really in working with NASA from a design and architecting point of view, conceptualizing the whole program from the very beginning. And so we partnered with James and his team at Trillium Technologies to put together what is now the Frontier Development Lab. So I'm going to show you a few pictures that help us tell this story. And by the way, I haven't seen many of you in a long time. You haven't seen me in a long time on these SETI Live events. So my name's Bill Diamond. I'm the CEO of the SETI Institute in Mountain View. And it's my distinct pleasure to be back with you today. And I know there's been lots and lots of SETI Lives since my last appearance, and hope you've enjoyed them and found them interesting and informative. And I do want to remind you that we bring these programs to you for your enhancement and inspiration and enjoyment. And we do so at, of course, no cost. We are, however, a nonprofit research and education institution. So we do, of course, appreciate when people come forward and help us out, including people like you. So if you're so inclined and would like to make a contribution to help the SETI Institute continue to bring this kind of programming to life, please reach out and do so. You can do that right on the Facebook platform now, and of course on our website at SETI.org. All right, so with that, let me jump ahead and share my screen here. Okay, and by now what you should see is some of our early FDL researchers at the NASA Ames Research Center in Mountain View, posing in front of the model of the space shuttle. And again, this is the FDL program. This is one of the early teams. I think maybe, James, this was the 2018 or 2019 team.
Yeah, 2018.
2018, right. And so again, this was a program conceived by the Office of the Chief Technologist at NASA back in 2015, and they had these things they wanted to explore, applying AI and ML to NASA's research priorities, exploring the efficacy of interdisciplinary teams working on short time horizons, and also whether or not we could get public-private partners involved in this program to help deliver NASA objectives of better, faster, and cheaper. So the Frontier Development Lab was born, and it really involves early career PhDs in machine learning and artificial intelligence, as well as early career PhDs in a wide range of relevant space research science domains. We also have AI and deep science subject matter experts and mentors or faculty that support the program. There are NASA stakeholders from various NASA centers and NASA science divisions and directorates. We have industry partners and academic partners. And again, what started as a partnership with the SETI Institute and NASA then became supported by Google Cloud, who have been absolutely transformative in bringing massive compute resources to bear on the FDL program, which has really enabled and facilitated the program so that our research—
That's why their logo is the biggest here.
That's why their logo is the biggest, and it should be. The program just really wouldn't be possible without Google, because the teams have real-time access to supercompute resources that they can iterate and problem solve, and that's really quite extraordinary. And we also have partners with a program overseas now, a sister program that James and his colleagues manage with Oxford University and the European Space Agency. And we have a wide range of partners, including some new ones not on this list, but like IBM and the Luxembourg Space Agency, Lockheed Martin, Intel, NVIDIA, the Mayo Clinic, and others. So it's really a program that has grown and expanded over many years. And we're going to tell you a little bit about the science and the kind of research programs that the teams have been involved in. But essentially what it's all about, if we look at, I'm just going to move something off my screen here. If we look at FDL a little bit by the numbers, and we can get this to work again. So this is our formula: 2 + 2 + 1 + 1 equals success. So we have 2 domain scientists with 2 AI ML researchers, a domain mentor for the science, and an AI ML mentor to support the compute. And these are the
math we do is normally trickier than this, isn't it, Bill?
Yeah, it's usually a bit trickier than this. This is one of our simpler formulas, and I think James will enlighten us into some of the more tricky stuff that gets going on. But this is already a year old. We're now in our 6th year. As of last year, we had gone 5 years with 8 research sprints on 2 continents, 192 researcher alumni, 47 projects, 47 machine learning workflows. We've got almost 30% women and 33% ethnic minorities.
We're now pushing those numbers. We're now 33% women.
See, even better. So that's why it's important to update these.
And 36% minorities, which is awesome.
It's what?
And 36% minorities now, which is awesome.
That's excellent. So we're making progress, and as you can see, it's kind of a 50-50 split between international and US participants. We have more than 17 partners now, and more than almost $2 million in donated compute resources. So really a transformative bit of numbers here. And this was last year's program where we explored.
So can I give you another stat?
Yeah, by all means.
And it's about the scale, the scale of the compute. And
yeah.
So when and this is again, thanks to our colleagues at Google. So a press release worthy level of compute is sort of above 50,000 nodes. When this is 50,000 computers linked together. Our record at the moment is 260,000. That's a really big supercomputer.
Like 5 times a newsworthy stuff, right?
You'd need a city block for that many. Yeah.
And I think another statistic we've talked about, James, is the compute resources that were applied last year compared to the first year. It was something like a 400x increase over the 5
700 times more.
700 times increase. So absolutely extraordinary. And yet even in the early years of the program, the teams were doing extraordinary work and truly groundbreaking AI and machine learning techniques. But the explosion in this area is well in excess of Moore's law, and it's really been
yeah. In the first year, which was our first partner was NVIDIA, which of course, and they still are. and we love them, and so do our researchers. In fact, our researchers normally manage to squeeze in an NVIDIA logo somewhere on their presentation.
Right.
Data scientists love NVIDIA for obvious reasons, because they invented the GPU, which powers artificial intelligence. But the box we had, which was still very powerful by the standards of the time, we only had one, and the teams had to take turns to use it.
That's
so
right.
It's quite
right.
Yeah.
Now it's cloud-based compute, but that first year it was hardware. It was a physical computer at the SETI Institute that was delivered by our partners.
Had a crank on it.
A mouse inside, I think. So I'm not going to spend too much time here, because I want James to go into a little bit more about what's happening this year. But in 2020, we had two teams tackling challenges in heliophysics, looking at solar storms, looking at star spots, and in terms of understanding stellar surface features of other star systems. We had 4 projects in earth science, mapping the waterways of the United States through satellite imagery, looking at predictive models for lightning and extreme weather events. Also, the Earth Intelligence Engine, which was really about, I think this was the one, James, of the coastal challenge, or was this the?
Yeah, this was satellite images from the future. So this was really exciting.
Yeah, this is the one predicting how coastal environments would change as a result of climate change. So basically generating future forecasted satellite imagery based on computer modeling applied to existing satellite imagery and plugging in variable data from new climate parameters. We also had a project in long duration missions for astronaut health, looking at something called causal inference in cancer research. In particular, this was colorectal cancer. So this was a sort of a medical challenge, and it was.
Well, they heard it just defined as like,
what's that?
As a casual inference this morning. So
casual inference, causal inference. But and so this brought the Mayo Clinic into the ecosystem of the FDL program, and was again truly extraordinary. So it shows the breadth not only of what we do at the SETI Institute in terms of the types of science that is undertaken here, but also of the FDL program itself. And we also had a challenge looking at lunar resources, where the metals are on the moon, which will be, of course, an important thing going forward as we bring humans back to the moon and potentially build longer term encampments on the lunar surface. So with that, I'm going to stop sharing my screen and want to talk to James and talk about what's going on this year. So James, we have, something else about last year. For the first several years of the program, for the first 4 years of the program, it was all in person. Researchers from all around the world came to the SETI Institute. The Trillium team and our partners were all here. And of course, having all of the, many of the industrial partners bringing in the technology and the AI ML expertise, being in Silicon Valley, in the Bay Area, made that really quite a dynamic environment. But last year, of course, because of COVID, we had to go virtual. And we were all concerned that, how could these teams working across 9 time zones in all kinds of different countries, never meeting together in person, possibly be expected to do the same kind of work that had been done in the previous 4 years. And yet, once again, they blew it out of the water. This year, we are, hopefully for the last time in the foreseeable future, virtual once again, but already seeing extraordinary results. So James, maybe you could tell the audience what kind of science is being done this year.
Yeah, it's super exciting. And over the last few years, we've started to kind of branch the work. So we're always looking for an opportunity to sort of build on what we've already done. So we're sort of building a portfolio of capacity. And I can show, I've got a slide that actually shows this, so perhaps I might bring it up as I'm talking. But we started with planetary defense, and we're always also looking for projects that are interrelated. So actually the planetary defense stuff is quite interesting because, if you're trying to deflect an asteroid, which I know a lot of this work gets done at the SETI Institute, Of course, it's useful to know what sort of rocket, or if you should use a kinetic impact or should use a gravity tractor. And we started using machine learning to figure out essentially what would be the best method. But of course, if you're going to shift an asteroid, you need to know what it's made out of, and you also need to know its tumble and its shape. And so we use machine learning to do shape modeling, and we use machine learning to figure out its tumble and its axis of rotation and all that sort of stuff. But one of the projects which we were really proud of, which is the one I'm going to start showing off right now, is using machine learning to really tackle a complex workflow, something which takes a lot of work by scientists, in this case, Peter Janeskins at SETI. And he used to do the job of tracking meteor and shooting stars at night by hand. This was something which would take hours of time. It would also mean driving up to the various locations where the observatory was and getting the cameras, and hugely laborious. This entire workflow has now been replaced by machine learning, and it's a very high TRL result. And when we had this working, I got a text from Peter, and he said, "You won't believe this, but there's a meteor shower happening tonight, and I'm already getting the evidence of the meteor shower on the system." And so this is what I'm going to show you now. Just share the screen.
Just as an explanation, the system that Peter runs, called CAMS, consists of hundreds of small individual cameras located in strategic locations around the world, aimed at the sky and looking for meteorites coming in from space. As many of you may know, meteorites tend to be the dust remnants of comets. So they're the long tail, if you will, of comets. And because comets have orbits around the sun, they're usually quite elliptical, but different than Earth's orbit. What happens is the Earth's orbit and the orbit of the comet intersect. And when they do, you get a meteor shower. And a program like Peter's can be used to trace back, using these multi-camera observations mathematically, where the meteorite came from, what originating orbit does it come from. And in some cases, we can use this to identify new comets that we've not yet otherwise directly observed before. So James, tell them what we're seeing here.
Yeah, so this is what we're looking at. So again, imagine the hard work, the laborious effort. All of these dots are meteor showers, but of course the ones that are clustered in the colors here, these are ones that belong to the ancient trails of comets. And of course, what's fascinating is that because the Earth is passing through these ancient trails, these are comets which are out beyond the Oort cloud. So these have, or in the Oort cloud, these have really long duration orbits, millennia. In fact, there's one of these, if you jump to the CAMS website, there's a cluster that was found recently, and this is from a comet that last passed by Earth in ancient Rome. So it's really cool to see how all these meteorites cluster. And of course, this would be impossible without a machine learning workflow. This is just far too laborious to be done by hand. But one of the reasons I wanted to mention it is this workflow has also been continually updated. It has to look for false positives, aircraft, fireflies, all of those random things, remove them, and then map it onto a 360-degree globe of the night sky. And this has now been reworked. So there's going to be a new CAMS going to be released very soon. But we're really proud of this. This is the most mature machine learning pipeline we've done. And it's great to see it being used like this. Another project, which I think you mentioned, Bill, was the fact that we do a lot of work on lunar exploration. And so this is super cool. You may have wondered sort of what it looks like inside a permanently shadowed region of the moon. This is the craters at the lunar poles, and they get virtually no light. Like they get a few photons, just the bounce off the Earth, or perhaps a bit of starlight. But these are immensely cold, immensely dark regions of the moon. But of course, because of that, we have a pretty good indication this is where there's likely to be water, possibly sort of frozen tundra. in the lunar poles. And this is probably where we'll be sending exploration in the next decade or so. And of course, the Viper mission from NASA is going to go into one of these craters in the next year or so. So what you're looking at is the application of machine learning to essentially make this crater like daylight. And so what it's doing is removing all the instrument noise. It's moving all removing all the noise from the data and creating a pretty crisp image of what it actually looks like inside these permanently shadowed regions. And of course, this is crucial for traverse planning, for figuring out exactly where to go, where to look. And this is really, again, a super exciting application of machine learning in terms of the ability to remove noise and make imagery which is useful for NASA missions.
And again, almost an impossible task if you think about it in terms of conventional compute or human based compute analysis of images like this.
You also mentioned the star spots, and I love this project because it just sort of, it's so exciting because it reminds you of how exciting space science is at the moment. And this is data from Kepler, but of course we'll be able to do this for TESS as well, which is the two missions which are looking at exoplanets. And of course we've seen this incredible, revolution in understanding the population of planets around stars, and that's super exciting. But the same data set also gives us star spots. And so this is what you're looking at. We're actually looking at the star spots of a distant star. Unfortunately, I don't know exactly which one we're looking at here. But why it's exciting is, of course, because we can map the rotation of these star spots, we can actually figure out the stellar rotation of stars. And this is really difficult. In fact, I think the number of stars that had been mapped, and we had a sense of what the rotation rate was less than 100. And so now we can do this. We have this workflow. We can essentially build out the rotation of all of the stars that Kepler and TESS are looking at. And this is projects that we're doing. This is an ongoing data set that we'll be producing. But again, it's a sort of example of how machine learning can take something that human beings can do, like Peter and his meteor analysis, but scale it up massively and automate that. And so it's very, very useful for science, because it's just taking a lot of the effort away, and meaning we can sort of ask questions at a much bigger scale than we ever could before.
I think it's, that's an important perspective is, AI and machine learning are not about replacing humans in many instances, except where we're talking about doing rote things over and over again, simply faster than humans could. But more importantly, I think they allow us to analyze data and analyze and understand phenomena in ways that would simply not otherwise be possible. So it's really about enabling new science and new understandings that conventional methodologies just wouldn't allow. So it really is about enhancing, not replacing, human scientific endeavors.
Yeah, and I think a lot of the anxiety people have about machine learning is this idea of humans being out of the loop.
Mm-hmm. Right.
But of course, when you're applying machine learning and AI to science, there's still uncertainty. And so that's why we always encourage human in loops at some point, whether it's active learning, creating some sort of system where there's still sort of human guidance, but those human capabilities are amplified massively by using technology.
Another one you want to
talk about, Candy? I'm not sure if this is, unfortunately this isn't animated, but it's, again, really exciting. And this is work that we did for our colleagues at USGS. And what you're looking at here,
US Geological Survey, for those of you unfamiliar, but they're kind of the American geologists, if you will, the government's geologists who understand the geology and topography of the US and its water systems, its mountains, et cetera. So go ahead, James.
Yeah, and so what you're looking at is a what's called a low flow stream. So this is approximately 1 meter or 2 meters wide. It's in the Colorado mountains somewhere. And these are mapped by hand or by foot. That's a better way of describing it. And it would, perhaps every 20 years, 25 years, this is when these maps would be created. The reason why they're difficult to map is that sometimes they're dry. And so, we don't know if there's water there or not. But because they're the sort of external, if you like, dendrites of the network, it's actually a vast amount of volume. In fact, it's about 50% of all of the volume in the US water network is actually in these low flow dendritic sort of streams at the edge of the web, if you like. And so it's really useful for drought prediction and just water stewardship for, in the case of the Colorado Basin here, this is servicing Las Vegas and California and all of the agriculture that happens in those regions. So it's really useful to know the volume of water in the system, but we don't have a way of doing this. And so what you're looking on the right-hand side is essentially a machine learning model, and the different colors are essentially showing the rate of flow in these low flow rivers. And so we can say, well, yeah, at the moment, this river has water, and we can calculate the volume in the system. And so we've improved the rate of data gathering from once every 25 years to once every day. Yeah. And this is using data from our colleagues at Planet. They have daily cadence from their Doves constellation. But because we're using that data from Planet, we can get a daily measure of the hydrology networks in the US. So this is super exciting. And when we showed this to folks in the water business, the institutional water management organization, they were like, this is the holy grail. We can't quite believe this is possible. And that's one of the exciting things about AI is, when it works, it's like magic, and it can be such a massive amplifier for the work of organizations like that.
And when you talk about data, the data that James mentions when he talks about Planet, this is a company previously known as Planet Labs. They're a company that has Earth observing satellites orbiting all the time. So the data we're talking about is Earth observation, so image data, and then using machine learning to interpret that data and learn from it, in this case, extracting the water network. And interestingly, when we first talked to USGS about this project, they told us that much of the American waterway, mostly the small little streams like this, the feeder network that feed into the larger brooks and streams that ultimately become rivers and are really the hydrology network, if you will, of the country, were quite unknown and not very well mapped and understood at all. So getting this higher resolution understanding of the fine little streams and brooks that feed the water system, and in particular, looking at the dynamics of this system in the context of things like climate change and global warming is hugely important. So it's been a fantastic project.
Yeah, so John Stock, who was the mastermind behind the challenge definition from USGS. When we originally wrote it, he was like, we should call it Where Droughts Come From, because it's true. Like if you know how much water's in the system, you can you get a good idea of the likelihood of drought. So it's extremely powerful, this work.
So we're at the bottom of the hour now, so we're not going to go on too much longer here, but I did want to pick out a few things in the chat, and then I'll have James talk about one other project here, what's going on in Europe. But quickly want to acknowledge some of our audience from all over the world that have joined us today. We have Liverpool in the UK, we have Odessa, Texas, and folks in Washington State, Montreal, Canada, Denton County in Texas, and Kentucky. People watching from Romania, from Vancouver, Canada, from Germany, from London, Atlanta, Georgia. We have a donation from Sabina. So I want to stop and thank you, Sabina, very much for being so kind to think of us and help us out here. So that's very much appreciated. We have Aotearoa from New Zealand.
Oh, that'll be probably my family.
Okay. I was going to say, speaking of New Zealand, I wanted to give a shout out to James's mom, who's we think is watching, And if she is watching, she's watching a day ahead of us. And so, as is typical of moms, they're always, one step ahead of us. So a big hello to James's mom.
And Dad'll be he's a big fan of SETI. He'll be
Oh, he's there too. So wonderful to have your dad and mom joining us. And we have Nish from Serbia. We have other folks from Canada. I do want to acknowledge a question that came in, an interesting question about if SETI doesn't think the moon contains life, why is it a research subject for SETI? It's a great question, and I will start by saying that the SETI Institute is, of course, looking for intelligent evidence of intelligent life beyond Earth, essentially on the thesis that if we're talking about intelligent and/or technological life, that is a life form that, in theory at least, can be detected or observed from great distances because its technology can be detected, whether that might be laser pulses or radio transmissions, et cetera. But it's not the only work of the SETI Institute. Our broader mission is understanding life in the universe at its most basic. How does it happen? Where does it happen? Under what conditions? What are the conditions of habitability that make life possible? And does it exist elsewhere? And while it's fair to say that the moon is, from our perspective, doesn't contain life, of course, the moon is also a stepping stone from a technology point of view to Mars. And Mars, as you know, is a planet where we feel very strongly life could have at one point existed, because Mars we knew was a warm and wet world at one point. And at one point earlier on in its existence, it had a heavier atmosphere and a magnetic field, which it no longer does. But there may also still be life on Mars. And so by going to the moon, we're prepping ourselves for putting boots on the surface of Mars, if you will. And we'd like to see the human presence on Mars doing science and doing exploration around the possibility that there's extinct or extant life on Mars. And so these are all connected.
There was the tidal hypothesis too, right?
What's that?
There's the tidal hypothesis too, about the fact we've got a relatively large moon and how it's created the tidal pools, which
that's true. Yes. Yeah, I mean, one of the things that you begin to understand when you start looking at how complex the notion of habitability is that everything matters. A moon that creates tides, that shifts the oceans, tectonic activity, volcanic activity, winds that distribute biology or prebiotic material or nutrients. All of these things matter and they all make a difference. So, understanding the Earth-Moon system, understanding the moon as an individual object, all of these feed our broader science of astrobiology, planetary science, and of course SETI endeavors. So that's a reason, and the moon is a fascinating place. And even we might have said some years ago that nobody thought there was water on the moon. Of course, now we know there is. So you can't rule anything out until you really go and investigate. So we'll come back and talk about this ESA project in just a moment, but all of this in today's episode, if you will, of SETI Live with James and I is a precursor to what's going to happen over the next 4 weeks. So our SETI Live series over the next 4 weeks is going to be a series of discussions with the actual researchers from the FDL 2021 program, and you'll meet members of each of the teams over that 4-week period, and have an opportunity to learn from and hear about their work in greater detail. And I think you'll be both amazed and impressed by the work that's being done and by the science that's being achieved and the new understanding and discoveries that are being enabled by applying the latest tools and technologies around machine learning and AI. So stay tuned for that. Of course, we'll be updating you all through our normal social media channels about these events, when they are, and what teams are speaking and what topics are being explored. So do come and join us for that. And James, did you want to say something a little bit about what's going on in Europe this year?
Yeah, let me. So I thought this is the last bit of eye candy, unfortunately, but
lots more eye candy to come, though. That's why we want everybody to come.
Yeah, exactly.
In the coming week.
So this is really exciting because as well as doing the stuff we've just seen, really enhancing work of scientists, machine learning starting to become a tool for prediction and integrating with numerical modeling. And so, when you think about weather forecasts, which is done with big supercomputers, and this is numerical modeling, it sort of hits a threshold point where it just gets too complex and too big for those methodologies. And so the idea is that, can we essentially replace numerical modeling with machine learning methods? And this is what you're looking at. And this is a precipitation forecast for the entire world. So you imagine how big that compute task would be 3 days in advance. So this is the ability to predict if it's going to rain or not 3 days into the future. And this is on parity with the fastest supercomputers in meteorology. So we can now, with machine learning, with much smaller levels of GPUs, match the capabilities of supercomputers. And I should qualify this, because the numerical modeling still beats this model when it comes to light rain or drizzle. But certainly in terms of whether it's going to rain or not, so basically yes, no, we can replicate those capabilities with machine learning. And this is really exciting, because it shows that in the future, there'll be the potential for this shift from sort of big scale numerical modeling to this sort of prediction, which is done with machine learning. So watch this space. It's still a very nascent area, but it's gathering momentum.
I'd like to think, James, that if we roll the clock forward far enough, we could get to the point where FDL is not just predicting the weather 3 days in advance, but maybe helping modify it. I mean, we could use a bit more rain in California. They could use a bit less on the coast. So that would be a dream.
But certainly it's a really exciting moment. And of course, then there's the idea that you can have numerical modeling, which is then informed by machine learning, and they start becoming these sort of symbiotic systems. And we're doing a little bit of that this year. In fact, I had, I don't know if you, before we wrap up, I could sort of take us through the teams that we'll be covering over the next few weeks.
Yeah.
And so here we have upgrading the solar wind. And so again, this is a great application of machine learning, because we have the Parker probe, which is now between Mercury and the Sun. We're getting really pristine, high resolution readings of the solar wind. And because we have that data, we can then go back through all the historical data sets of the solar wind and upscale them to that same resolution that the Parker probe is getting as it approaches the Sun. So this is a really, again, another cool thing that machine learning can do. It can be used to enhance data sets. The second project is solar drag. So this is the pernicious challenge of understanding where our spacecraft are going to be as they're orbiting the Earth, particularly low Earth orbit, because of the drag which is caused by the bloating of the atmosphere, which is of course affected by the Sun. I mean, there's a few other factors too, but certainly the extreme ultraviolet is one of the biggest factors. And so this project is looking at that and seeing if we can better predict the position of spacecraft, which of course has implications for deorbiting spacecraft, for management of the ISS, but also for managing space traffic management. And then there's the astronaut health project, and this is the one we're calling causal inference, which is essentially a machine learning technique where you can start looking at all the different actors in a complex system, and you can then determine which are the most, if you like, active variables in that complex system. And so we can look at a problem, for example, cancer, and say, well, of these 10 or 15 complex interlinked factors, these are the 3 factors actually causing this issue, this healthcare issue. And so we're applying the same methodology to looking at the health of astronauts on long duration missions. And then lunar resources, we're using a methodology called super resolution to look at the areas where Artemis is going to, where the mission is going to land in the next decade, hopefully, and we're super resolving that data so we get much crisper and clearer maps for that next generation of exploration. Lightning upgrade, this is looking at data coming off a geostationary satellite and saying, can we upgrade the quality of that data set? And why that's important is if we can get a high quality level of, is it flash rate? Yeah, it is flash rate, on the frequency of lightning. This means we can better predict tornadoes and hail. Automated reporting, this is the ability to use natural language to look at an image and turn that into text. And so if you like looking at a picture of the coral reef, it'll say this is a coral reef and the water is blue because of algae, or it's got white caps because it's windy or whatever. But basically getting the ability of a machine to look at an image and write the text. The digital twin of the coasts is essentially trying to understand storm surge and how water behaves in different conditions. And then in Europe, we're looking at super resolution and embeddings for tools for the World Food Programme. And lastly, machine learning payloads is looking at the ability to use machine learning onboard spacecraft that hopefully will return insight back to Earth very rapidly. So that's the portfolio. Again, as Bill said, we'll be meeting all the teams over the next few weeks, and it'll be a chance for everyone listening to really dive into the science, and there's always good conversations. And also, I think if you're interested in machine learning, there's no better way of learning than listening to our researchers as they're grappling with these problems.
Yeah, absolutely. That's great. Well, that's so stay tuned. These are the subjects that the teams will be talking about over the next couple of weeks. And James, if you can stop your share, I'll do one last bit of eye candy that brings us back to the CAMS project, because it's just kind of amazing what can be done with data visualization techniques. So what you should now see, are you seeing the CAMS model?
Oh, yeah.
Yeah. So this is showing you the colored rings in the middle of the screen. The bright dot is the sun, and the colored rings are the inner planets. The white dots are all individual meteorite observations by the CAMS system, and which has traced them back to their originating orbit. I mean, we can zoom out of the solar system here and see the actual orbit of this particular comet. We can rotate to see that it is on a different plane, a different angle than the plane of the ecliptic, or the plane in which all the planets are located. And you can see how far out into the solar system it extends. And there's a data set like this and a visualization of the data sets for each of the major meteorite events that are in the database. So this is how data visualization is also so impactful and can be so beautiful as well as informative to the science. That part of the CAMS project that James mentioned. You can see more about that at cams.seti.org. So with that, I'm going to stop my share. We're going to wrap it up for today. James, I want to thank you again for staying up late in the UK and joining us tonight.
My pleasure.
Thank your
family.
family.
We get to talk about space and computers and geek out. And yeah, no, really happy.
Exactly.
And also, Bill, my sisters are watching too. So
yeah, sisters were joining us as well. So hello to them. And with that, again, a reminder that this program, SETI Live, is brought to you by the SETI Institute in Mountain View, California. And you can learn more about our work at SETI.org. You can sign up for our monthly e-newsletter called Journey, which takes you on a journey of all the kind of science and exploration that our researchers endeavor to do day in and day out. And you can support us if you are so inclined. We're always grateful to help that allows us to continue bringing this program to you. So our crack communications team, I want to thank Jasmine and Beth and Rebecca for bringing this together today, and you'll be hearing from them in next week and beyond about the programming upcoming. So we're going to do a 4-week series, a deep dive into FDL, and we look forward to seeing you all on those future events. And I think you'll be amazed and inspired by what you see.
Bill, there's one other group I should have mentioned. So all of the researchers who did the work that we showed today, just like to say thank you as ever for the incredible work. And then if people watching are interested, We open source everything. It's all on FDL.ai. And you can also go to spaceml.org, which is where we host the data sets. But again, just thank you so much to the researchers and the faculty, and of course our partners.
Yeah, they're all extraordinary. We couldn't do the program without them. And in fact, you can also learn more about the Frontier Development Lab program itself at frontierdevelopmentlab.org. So lots of sources of information. It's an amazing program. We hope you'll tune in next week and then over the series and learn more about it. And in the meantime, thanks very much and goodbye from Mountain View, California. And James, thanks to you, and good night to you in London. And we'll look forward to seeing all of you in a future episode. Take care, everybody.
Thanks, Bill. Thanks, everybody.
Thanks, James.